All right, guys, we've made it to part B2, which are questions 51 through 65. From now on, all of your answers for questions in parts B2 and part C are going to be put into your answer booklet, which comes with your test. And I just want to show you a copy of that. It's right here. This is the answer booklet. You'll fill this out at the beginning of the test and put all of your answers in here. And just a heads up, and we'll remind you of this, all of these answers must be done in pen, except for any drawings that you might do. Like, for example, question 51, you could do that in pencil if you wanted to, but all the other answers must be done in pen. So just a heads up on the rest of these questions. They're all going to be short answer. So let's start with question number 51. 51 is a pretty simple question, and you'll notice that it's just constructing a line graph by plotting the percentages of the disintegration product. So specifically, we're just looking at these numbers, what is true of those numbers on your graph. And so you would just plot those on a graph. So I have the graph right here. I would use a pencil most likely to do this, but I'll just show you. It says to plot the disintegration product for all of the times given. So at time 0, it is 0. At time 1.3 million years, or billion years, that's a half-life, it's at 50, okay? And then at 2.6 is 75. And so on and so forth. And so you just plot these as best you can on there and then connect all the dots. I didn't do that last one very well. Okay, so that is your graph for question 51. And we're just looking for that basic shape when we're grading that. Okay, so question 51, just straight up line graph. Question number 52 is asking for the name of the radioactive isotope that's shown in our graph. And you'll notice that that kind of is based upon the graph we just drew. And specifically, we can figure this out by recognizing when the half-life is. The half-life of this isotope is when they both meet at 50%, and that's at 1.3 billion years. And so we would use our reference table, and sorry, let me go to the actual reference table, specifically page 1 of the reference table. And we're looking for 1.3 billion years for the half-life. Now remember, this is times 10 to the 9th is a billion years. And so the answer to this question is just potassium 40. So that just comes directly from your reference table. So potassium 40 or K40 is the name of the isotope. Now, the last question, number 53, says to calculate the amount in grams of an original 300-gram sample of radioactive isotope remaining after 3.9 billion years. So if you think about this, it's actually shown right here on the graph. This is 0 half-lives, this is 1 half-life, 2 half-lives, 3 half-lives. So we go through 3 half-lives to get to that 3.9 billion year mark. So if we start with 300, and after 1 half-life, or 1.3 billion years, we're down to half of that. So that would be down to 150 grams. And then after 2 half-lives, we'd be down to half of that, which would be 75 grams. And then after another half-life, we'd be down to half of that. So what you would have to do is basically just take 75 and divide it by 2, and that will give you your answer, 37.5 grams. And that's the answer to question number 53. All right, questions 54 through 57 are based upon this weather map, and some isobars are shown on here, as well as a couple of fronts. There's a cold front and a warm front on this map, and we're going to be answering some questions based upon the weather. So question number 54 is kind of a two-part question. You have to talk about the air pressure, as it says, what will happen to the air pressure by the time the cold front reaches Syracuse, and the cloud cover in Rochester. So currently, the air pressure in Rochester is somewhere between 1,000 and 996 millibars. And we can tell that based upon the fact that the 996 line is here and the 1,000 line is here, and it's somewhere in between there. And you can see that it's in the shaded region, which means it's pretty cloudy there. So if this whole entire system moves like all weather systems do, we would expect the entire thing to move off to the east, and therefore this center of this low will be over here near Plattsburgh, and everything will shift. That means that the pressure will probably rise because whatever is over here in this area is going to come towards Rochester. And so we would expect that the pressure should increase. And I'm just going to write that down, that the pressure should go up. Okay, increase pressure. Not a whole lot, but it should go up a little bit. And then if you kind of think about that, if that whole entire system is moving off to the east, the cloud cover, which is in Rochester currently, is going to be gone. The clouds will lift. It's probably either raining or snowing, depending upon the time of year right now, because it's on the cold front. And it's most likely going to lift all that cloud cover off based upon the fact that the pressure, the high pressure, is moving in. And so you'd expect the cloud cover to decrease. Cloud cover will go down. I'm just going to draw an arrow down. Okay? And that's just based upon the fact that all weather systems move from the west to the east. Question number 55. 55 is a station model of Buffalo, New York at the time the map was prepared. And you can see in Buffalo, New York, the cloud cover is actually less. So that kind of goes along with the previous question. But what we have to do is we have to record all the weather data that's given to us in this station model. And this is technically a reference table question, ESRT page 14. And we'll take a look at that in a second. But we have to record all of the information for this station model. Okay, so let's take a look at our answer booklet to see what we need to record. Our answer booklet gives us this, and we have to record the air temperature, the pressure, the wind direction, and the wind speed. So let's start with the air pressure, the air temperature. The air temperature on our reference table, as you can see, here's the station model explanation. The air temperature is in the top left. So this number up here is the air temperature. So if we go back to our test, the air temperature is right here. That's 72 degrees. Okay, so I'm going to write 72 degrees into our box here, 72. And we don't need to label it because it's already labeled right there, so 72 is good enough. The barometric pressure in millibars. Now this might be the tricky one. Let's just kind of look at our reference table first. The pressure is here, and remember, it's a coded pressure, meaning it's a 3-digit number. We have to decode it. So we have to put either a 10 in front, like is shown in this one, or a 9 in front. So let's take a look at what it says in our test. It gives us 0, 1, 0. And so either our pressure is going to be 10, 0, 1, 0, with a decimal right there, or 9, 0, 1, 0, with a decimal right there. And so which one is it? Which one are we actually going to record? Well, the trick to this one, if you recall, is to actually look at your reference table. On the same page, I'm going to go back to that. If you look up above, sorry about that, let me scroll up here. Look at our pressures that are on this chart in millibars. Is 901.1 on there? And the answer is no, you don't see this on our pressures. The lowest pressure is 968. The highest is 1040. So the other pressure that we recorded is probably the correct answer. So let's take a look at what we recorded. 1001.0 has got to be our pressure. Let's record that on our answer booklet, 1001.0. Okay? And remember, you just have to put the 10 in front. The biggest mistake with that question is to just record what's written, the 010. And remember, that's the coded pressure. We want the actual pressure. All right, wind speed, wind direction. So if you look at our test, you'll notice that the wind speed is right here, and the wind direction is right there. And that is pointed to the northwest. If you think about straight up as north, right? That's north. This would be northwest. So our wind direction is from the northwest. And our wind speed are these feathers. So let's take a look. First, I'm going to write northwest right here so I don't forget. Our wind speed are the feathers. There is one long one and one short one. And if you look at your reference table tells you that the wind speed is given by the feathers. A whole feather is 10 knots, and a half a feather is 5 knots. So in our case, it's actually the same diagram, and therefore the total wind speed is 15 knots. So I'm just going to write that on my answer booklet. The wind speed is 15 knots. The biggest trick with this one is recognizing that even though this is pointing to the northwest, that's where the wind is coming from, and it's blowing into our weather station like that. Okay, so that's number 55. All right, question number 56. The relative humidity at Albany when the air temperature is equal to the dew point. That's key, equal to the dew point. What is that? And that's something that you can either memorize, you can kind of get some hints from your reference table. Specifically, page 11 of your reference table has stuff about dew point and relative humidity. We'll take a look at that in a second, but let's just look at Albany at the moment. You'll notice Albany hasn't had the warm front yet, but it is 100% cloud cover. And that's kind of helpful just to realize that it's probably raining in Albany, but it's 100% cloud cover. Now let's take a look at the reference table just to get some hints here. The dew point equal to the air temperature. What's true when that's true? Well, if you look here, all of these are indicating that the air temperature is equal to the dew point, meaning 26 equals 26 or 28 equals 28. And when that's true, if we go down to our bottom table, you'll notice that that just means that that's 100% humidity. You'll notice all of these here are 100% humidity. So it's complete cloud cover, 100% humidity. The air is completely saturated, however you want to say it. The answer to this question is 100%. Okay, so that's number 56. Number 57, the name of the weather instrument used to measure the wind speed at Plattsburgh. That's a tricky question just because you have to remember this. You have to know your weather instruments. And this one in particular is a little bit tricky because it's got a hard name. The name of the instrument is called an anemometer. Now, if you're like, I'm not going to remember how to spell that on the Regents exam, no worries. You just got to get close enough and we'll give you credit for it, okay? Anemometer is the answer for the instrument that measures wind speed. Other instruments, remember, a thermometer measures temperature, a psychrometer measures humidity, a wind vane or a weather vane measures the wind direction, and a barometer measures air pressure. So those are the other weather instruments, but that's the answer to number 57. All right, questions 58 through 61 are based upon this diagram and a little bit of a reading about the orbits of Earth, a comet called Tempel-Tuttle, and planet X, which is not identified. So we just have to answer some questions based upon this paragraph that's here. It gives you some information about this comet Tempel-Tuttle, tells you how far away it goes away from Earth and what we see. And you'll notice how small Earth's orbit is compared to the orbit of comet Tempel-Tuttle. And you'll notice also that the comet's orbit is very stretched out oval shaped. We call that very elliptical. And remember, in an ellipse, you have this stretched out kind of circle, and one of the foci is always the sun, okay? And the other foci is just some random spot in outer space. And if we were to draw this ellipse, we'd stretch the string over top of those two push pins and drag it around, and we'd get our ellipse. And remember, this is very, very elliptical, which means its eccentricity for this is probably closer to 1, right? Or close to 1. If it's more circle-shaped, if it's more like that, the eccentricity would be closer to 0, okay? And you can kind of think about that, that it's more circle-shaped, so its eccentricity is closer to a circle shape like 0, okay? So that's just initial stuff to think about. Now let's take a look at some of the questions. Question number 58, identify the name of the object located at one of the foci of the elliptical orbit of comet Tempel-Tuttle. Well, I kind of gave you the answer to that. Remember, always, one of the foci is the sun, okay? Because it's orbiting the sun, one of the foci is always the sun. So that's the answer to number 58. That's just something you're going to have to know. Number 59. Number 59 is asking about a solar system planet represented by planet X, which orbits near comet Tempel-Tuttle's farthest distance from the sun. So we're looking for an actual planet in our solar system, which means we're going to have to go to our reference table. But let's just take a look at where is the comet Tempel-Tuttle farthest from the sun. Well, it tells us right in the paragraph right here. The sun, it ranges from 145 million kilometers at its closest point to 2,900 kilometers at its farthest distance. So we're looking for an orbit of a planet 2,900 million kilometers away. So now let's go to our reference table. Specifically, I'm on page 15 of the reference table. You'll see the chart here. So we want something close to 2,900 million kilometers. And remember, here's our distances. They're all in million kilometers. And we want a number that's close to 2,900. That would be Uranus. There you go, 2871. The answer to this question is our planet Uranus in our solar system. So I'm going to write that down. Uranus, Uranus. Okay, so that's the answer to number 59. All right, question number 60. Determine the year in which Comet Tempel-Tuttle will next make its closest approach to the sun. And this one comes directly from the paragraph. We're going to have to do a little bit of calculating here, but it does tell us that the most recent approaches to the sun occurred in 1965 and 1998. And so what we're just going to do is figure out how long is one revolution. In other words, how long apart were those years? 1998 minus 1965. And if you do the math there, you're going to get 33 years for one revolution of this comet. It takes a pretty long time to go around the sun. Now, the next time it's going to come close to us would be 33 years after 1998. And so we're just going to add 1998 to this to get our answer. And if you do the math, 1998 plus 33 years gives you the year 2031. And so the answer to this question is 2031, so it's about 10 years from now. Okay. Number 61. Identify the force that causes debris from the comet to fall through Earth's atmosphere. To fall, right? Things that are falling back down to Earth are falling because of the force of gravity. So that's just kind of a common sense question. Didn't really require a lot of earth science knowledge. You just have to know that gravity is the force that makes things go towards Earth and draws things towards the center of Earth. Okay, so that's number 61. All right, questions 62 through 65 are based upon this diagram of an observer looking at the sky, and you can see there's a picture of this man standing there, and there's the position of the sun going across the sky, A, B, C, and D. And you also have a location of Polaris on here, which is important. That'll come into play later on. Notice that this is June 21st, and notice where Polaris is located. You can see it in the northern hemisphere, which means this person is standing in the northern hemisphere. The Polaris is in the northern sky. The angle of Polaris above the ground is 23.5 degrees if you look at that precisely. That's helpful. We'll look at that later. Okay, so first question, number 62. Describe the changes in the length of the observer's shadow as the sun appears to move from position A to position D. So in the morning, the sun's right here, and if it's right there, it's going to be shining on this person, and they'll have a shadow over here. It's going to be pretty long because that sun is really low in the sky. But as that sun gets higher in the sky towards B, this person's shadow will now be pointing basically due west, and it'll be a little bit shorter because the sun is higher in the sky. At C, up here, he's going to have absolutely no shadow because the sun is shining right down on him. And then back at D again, when it comes back down the other side, he's going to have a shadow pointing over here that's kind of long. Okay, so it will start off at A, very long, okay, long shadow. And then at B, it'll be shorter. And then at C, no shadow. And at D, it will get longer again. Okay, and you could describe that in paragraph form. You can describe that in a sentence or two. You could describe the direction of the shadow, where it's pointing. Basically, you just need to tell the changes along that path from A all the way to D. Okay, so that's kind of the answer to number 62. You have a little bit of freedom there in your answer, but that's essentially what we're looking for in that answer. Okay, question number 63. How do we know that this observer is located at the Tropic of Cancer? Tropic of Cancer, if you recall, is 23.5 degrees north. Now you're saying to yourself, well, how do you know the Tropic of Cancer is 23.5 north? Unless you memorize that, you have a way to tell. You just have to use your reference table. So I'm going to zoom out. I'm still on my solar system data chart. I'm actually going to go to a chart on the reference table, which has absolutely nothing to do with the question. It's the ocean current chart. And if you look at this thing, it tells us the Tropic of Cancer is 23.5 degrees north. And so we know that the angle of Polaris has to be 23.5 degrees above the horizon. So one possible answer is that the Polaris is at an altitude of 23.5 degrees. And the fact that you can actually see Polaris means he's in the northern hemisphere, okay? That's one answer. Another answer you could say is the fact that this observer has the sun directly overhead at noon on June 21st. So I'll just say sun overhead at noon on June 21st. Sorry about my sloppy handwriting, but you get the general idea. Okay, so those are two possible answers. Either one of them will get you credit, but basically you have to give some evidence as to why that person's there. Number 64, state the number of daylight hours at this location on September 23rd. Well, on September 23rd, you might recall that that is the equinox, and equinox means equal night, right? Equal daylight to nighttime hours. And if you divide it in half, 24 hours in a day, that would be 12 hours of daylight. And that's true for everyone on Earth, not just this person, but everybody. No matter where you are, you'll always have 12 hours of daylight on September 23rd and on the vernal equinox on March 22nd. Okay, so 12 hours is the answer to number 64. Okay, number 65. The sun's apparent movement through the sky is caused by the Earth rotating. We know that, but we want to identify the device that was first used to demonstrate the fact that the Earth rotates. The answer to this question is kind of one of those memorization things. I taught you in the classroom that the device that they used to first determine this is called the Foucault pendulum. And so you're just going to have to recall that. That will pop up in more than one way. Sometimes it's a short answer question like this one. Foucault pendulum was a device used to measure the Earth's rotation.